Welcome back, Form 4s, for our 7th lesson under electrochemistry. And today we want to look at a complete electrochemical cell. The objective is to define a complete electrochemical cell or a voltaic cell, and then also to describe the anode and the cathode. So to identify the anode and the cathode and to describe them. So, let us move on so that we can understand what a complete electrochemical cell are. Now, last time we talked about electrode potentials, how to measure electrode potential of different half cells. Today, we want to look at how to measure the electrode potential of cells when they are combined, when two cells are combined. In our last discussion, we said that when zinc, in our last discussion, we had the zinc, a half cell, dipped into a solution of, so this is a half cell where we have zinc solid dipped into a solution of zinc sulfate, aqueous. So this one here is zinc half cell, and we say that when a metal is dipped into a solution containing its own ions, then a potential difference will be established between the metal rod acquiring a negative charge and the solution acquiring a positive charge. The metal rod acquiring a negative charge and the solution acquiring a positive charge, what we call electrode potential. It is not easy or possible to measure the electrode potential of one half cell. Therefore, to measure the electrode potential of one half cell, we have to combine it with another cell. For example, on this side, we can have another half cell. Let's say on this side, we can have this side, we can have copper solid dipped into copper 2 sulfate. Copper solid dipped into copper 2 sulfate. So we have two half cells. So for us to measure the electrode potential of one half cell is not possible. We have to connect it to another one. So we connect this using a conducting wire. So this one is a conducting wire, and this one is voltmeter. So we use a voltmeter to measure the voltage. Now, still something is missing. These two solutions must be connected for electrical current to flow. So in this case, the two solutions are normally connected using what we call a salt bridge. So we take a tubing, and in this tubing we place a salt. We can place potassium nitrate, potassium chloride, sodium chloride. So let's say we are using potassium nitrate. Then here we block using cotton, thick cotton. So we have connected the two solutions. This glass tubing with potassium nitrate solution inside is what we call a salt bridge. We call it a salt bridge. So we are saying that electron potential is measured when the concentration, if you want to measure the electron potential, the concentrations of the two electrolytes must be 1 molar and the temperature must be 25 degrees Celsius. The temperature must be 25 degrees Celsius. So remember, for experiments to be fair, there must be standard conditions. So in this case, the standard conditions are 2. 1, the concentration of the two solutions must be 1 molar. 1 molar zinc sulfate, 1 molar P2 sulfate. Then the temperature must be 25 degrees Celsius or 298 Kelvin in the Kelvin scale. That is what we have. Now, this one is now called zinc copper electrochemical cell. So we are saying it is not possible to measure the electron potential of an element, but it is possible to measure the difference in potential between two half cells. It is possible to measure the difference in potential between two half cells. For example, zinc half cell and copper half cell. Now, so when we talk of a complete electrochemical cell, it is a setup consisting, a complete electrochemical cell is a setup consisting of two half cells connected by a conducting wire and a salt bridge containing a salt solution. So a complete electrochemical cell is a setup consisting of two half cells connected by a conducting wire and a salt bridge containing a salt solution. Or we can say that a complete electrochemical cell is a combination of two half cells which produce electric current or which generate electric currents due to redox reactions. We are going to see that in these two cells, a redox reaction is taking place which generates electric current recorded in terms of voltage. So the voltage recorded there is equivalent to the electron potential of one of these cells. Now let us move on and now talk of electron potential of a cell. So when we talk of electron potential of a cell, this is the recorded voltage when two half cells are connected by a conducting material and a salt bridge. That is what we call electron potential. Normally it is denoted by E naught. E naught. So we move on and study the zinc copper electrochemical cell. Zinc copper electrochemical cell. Now, what will happen? What chemical changes will take place when you have zinc copper electrochemical cell or voltaic cell? Now, this side, in the zinc is more reactive than copper. So what happened? This rod, which is zinc, the atoms here will form ions by losing electrons. That is what will happen on this rod. Now, before we connect them, let's say there's a gap here. So before we connect them again, the copper, this copper again, will lose electrons to form copper 2 ions. The copper losing electrons to form copper 2 ions. But do they have the same reactivities, these rods? No, they do not have the same reactivities. The more reactive metal will lose more electrons, will release more electrons per minute than the less reactive copper. So zinc will be losing, let us use figures. Let's say zinc is losing 1,000 electrons per minute. And copper can only lose 500 electrons per minute. So what will happen? Here, after 1 minute, for example, after 1 minute, we'll have 1,000 electrons. After 1 minute, we'll have 500 electrons. So the electrons will start migrating. This one, on copper rod, electrons will migrate this way. On zinc rod, they will migrate this way. So that when you connect the two half cells, then there will be one problem. Electrons cannot move towards opposite directions. One side must release electrons, the other side must accept electrons. So here we have higher electron pressure. Higher electron pressure. Why? Because we have more electrons. This side we have lower electron pressure. Why? Because we have fewer electrons. So automatically, obviously, electrons will flow from higher electron pressure to lower electron pressure. So electrons will move from the more reactive electron to the less reactive electrons. Now, because of that, things must now change. If this side, if electrons must move this way, then this side electrons will be lost. Zinc rod will continue to lose electrons. Then, in this solution we have copper 2 ions. Copper solid, a copper solid cannot gain electrons. Copper atoms, a metal cannot gain. What can gain are metal ions. So this equation will change. This one will change, such that we'll have copper 2 now gaining electrons to form copper solids. So you can see that on the left hand side, on zinc electron, electrons are lost. Loss of electron is oxidation process. On this side, the copper 2 ions in the solution are gaining electrons. Gain of electron is reduction. So oxidation occurs on the zinc electron and reduction occurs on copper electron. The electrode where oxidation occurs is what we call the anode. So this one will be the anode. The electrode where reduction occurs is what we term the cathode. So the copper is the cathode. Then we have more electrons on this zinc electron. More electrons on zinc electrode. Because we have more electrons and electrons are negative. Electrons are negative. So this anode is the negative electrode. We have more positive charges on this copper electrode and less electrons. So it is the positive electrode. Therefore, if we compare this one, later we compare this electrochemical cell with electrolytic cell, you'll realize the differences. So, at the anode, we have oxidation. At the cathode, we have reduction. So the next thing is to write the overall redox equation. For us to write the overall redox equation for this cell, we will take the two half-cell equations. So we'll take zinc, changing into zinc plus 2 electrons. This one. Then we come to copper. Copper 2 gaining electrons to form copper. Then we add. Remember, this first one shows loss of electron, which is oxidation. This one shows gain of electron, which is reduction. So when we add them, we collect the reactants together. Zinc, copper 2, and 2 electrons. We have zinc, copper 2, and 2 electrons. On the other side, product side, we have zinc 2, 2 electrons, and copper. Zinc 2, 2 electrons plus copper solid. We cancel the 2 electrons. We remain with zinc solid plus copper to give zinc plus copper solid. So this one is the overall cell reaction showing oxidation and reduction process taking place simultaneously. Therefore, this is a redox reaction. Redox reaction. A redox reaction is a reaction in which oxidation and reduction occurs simultaneously. So the overall, that's how we come up with the overall cell reaction. The overall cell reaction. So from there, we are saying that the half cell on the left consists of zinc electrode immersed in zinc sulfate. Zinc electrode immersed in zinc sulfate. Then the half cell, the one on the right, this half cell on the right contains copper electrode immersed in copper 2 sulfate solution that we have. The electrons are then connected by a conducting wire which pass through the voltmeter, Then we have seen that. Then the two solutions are connected by a salt bridge containing potassium chloride or potassium nitrate, can be sodium chloride or. Now the salt that is used in the salt bridge should contain ions which cannot form insoluble salts with the electrolyte. Salts, any salt which contains ions which cannot form insoluble compounds with the electrolytes. Then another thing we have discussed is that before the two half cells are connected, each of them builds a layer of electrons around it. So you have a layer of electrons here, a layer of electrons there, around it. Then one of the half cells are connected. One of the half cells, once the half cells are connected, electrons flow from the electrode with a higher reactivity tendency, to lose electrons, that is higher electron pressure, to the one which has a lower tendency to lose electrons, lower electron pressure. We have also seen that. Then electrons therefore flow from the zinc electrode to the copper electrodes. Then the other thing that you should note is that zinc electrodes gradually dissolve, forming zinc ions. So this zinc electron will ionize. The solid here will ionize according to this equation. So it will remain smaller and smaller. The mass will decrease. So the mass of zinc therefore decreases. But what will happen on the copper electron? Copper 2, remember the color of copper 2 sulfate solution is blue. Why? Because of the presence of copper 2 ions. But what is happening to the copper 2 ions? Copper 2 ions are being discharged to form copper solid. So this solution the blue color of this copper 2 sulfate will fade because the blue copper 2 ions are being used up. And these copper atoms will get deposited on the surface of the electron. So the mass of the cathode electron will increase due to deposition of copper metal. Another thing, so the concentration of the zinc ions in solution will increase as zinc ionizes. As zinc ionizes. And again, electrons flow through the wire to the copper electron where they are accepted by the copper 2 ions, forming copper atoms, which are deposited on the copper electron. Therefore, the mass of the copper electron increases. And the concentration of the copper 2 ions in solution will decrease. We have seen that, making the copper 2 sulfate to turn from blue to colorless, or the blue color will fade. This one is the half equation at the copper electron. Then we have the overall equation, which we have written down here. You've seen it. Now, in this case, zinc is the one that donates electrons. A substance that donates electron is the reducing agent. So zinc here is the reducing agent. And the substance that accepts electrons is the oxidizing agent. The oxidizing agent is copper 2, not copper solid, but copper 2 ions. Because it is the copper 2 ions that accept electrons to form copper atoms. Now, the flow of electrons, what will happen now? This flow of electrons will result, we have talked about the recorded voltage. The flow of electrons result in an electric current, whose magnitude is equal to the difference between the electrode potential. So the difference in the electrode potential between copper and zinc, that difference will be equivalent to the magnitude of the electric current that will be recorded there. So this value obtained, the value that is obtained is the potential difference of the two half cells. The value obtained here is the potential difference of the two half cells. Now next we look at the magnesium copper electrochemical cell. Magnesium copper electrochemical cell in our next video. Thank you for listening and watching.